Organic identity questions or mixed spectroscopic technique are, in my opinion, the hardest. So these styles of questions, you're probably already familiar with them. They come at the end of an organic paper and you have to identify an unknown molecule given a series of clues, which usually is some information about the mass spectra, the NMR, proton and carbon NMR, infrared, and then maybe some chemical tests or empirical formula information. You put all those clues together and then you work out the identity of the molecule. Easy, huh? Well, let's take a look at this example today. Make sure you have your data sheet to hand and your periodic table. If you don't have a data sheet, I've attached the one I'm using for this lesson. Otherwise, let's get into it. This question is about compound T, CXHYOZ. So we've got to work out the identity of compound T. And you can see in the first bit, we are given mass spectroscopy information there. We have some infrared information there. And then an NMR spectra at the end there. Usually these questions, they're around, they can be up to 10 marks, so quite a lot once you put all of this stuff together. So part of the mass spectrum of T is shown below. The peak heights of the M and the M+1 peaks are 33.9 and 3.4 respectively. Calculate the value of X, the number of carbon atoms in T. So just a quick recap for mass spec. The last peak in the spectrum, this one, is described as the molecular ion peak. And what does it tell us? It gives us the mass of the molecule. So the RFM of the molecule, basically. And we can see that this molecule has a mass of 150. However, if we look closer, we can see, right, if I get rid of that annotation, you can see, if I zoom right in, there's a tiny peak there. And that looks to be at about 151. So when this happens, right, it's always indicative that there are isotopes present in the molecule. So the one that would fit that formula there would be, well, the obvious one would be carbon-13. In substances which have carbon, about 1.1% of the carbon atoms will be carbon-13. So the vast majority are carbon-12, and a tiny amount will be carbon-13. And what we can do is we can use a formula to calculate the number of carbons in the atom. And it's a really simple formula, so I'm just going to rewrite the formula here that we're going to use. So N, where N is the number of carbon atoms in the molecule, is equal to 100 times the abundance of the M+1 peak, all divided by 1.1 times the abundance of just the molecular ion peak, so the M+ peak. Where 1.1, that number comes from, as I just said, about 1.1% of all carbon atoms are carbon-13. So let's use the numbers they provided, so 33.9 and 3.4. So we have N equals, and don't forget you're going to need your calculator for this if you're working along with me. So let's put that in, gives us, so approximately 9 carbons. Okay, so we know there's 9 carbons in this molecule. Now let's turn our attention to the infrared. So it says the infrared spectrum of T is shown below. And if you look at my previous lessons on infrared, again, the link for those videos is in the description below. I said when you see this little bit here, it's usually indicative of either an aldehyde or a ketone. But there's other peaks you can look out for that really sort of give it away. And the first one that jumps out to me here is this one, V. So you can see that's at about 1500, 1600, 1700. Anything around the 1750 region is always going to be the same thing, which is C double bond O. And then this one at W, what is that at? That's 1001, 1002, and then 1003. So it's just before 1003. If we look at the data table that I've attached below, we can see that 1000 to 1350. There's a couple of options, so we can rule out some of them. So we can see the fluoroalkanes have a shift in that number. Well, there's no fluorine in the molecule, so we can rule that out. And we have the alcohol stretch is also there as well. It's a C single bond O, which is present for alcohols, esters, and carboxylic acids. Now, it's definitely not going to be a carboxylic acid because the carboxylic acid usually has a really broad inverted peak like that on the left, called the inverted mountaintop, which is what I referred to it in my previous video. And that gives it away as a carboxylic acid. That is absent, so it's not a carboxylic acid. So that leaves us with the possibility of an alcohol or an ester. Alcohols, again, have a really distinct peak on the left. They have what's this described where the peak goes down, comes back up, goes down again, and comes back up again. This idea of a double dip. This is not present, so this cannot be an alcohol. So it's probably going to be an ester, but we don't know enough at this point. So that peak there is C single bond O. And then just doing a quick scan through the remainder of the table, there's nothing else in that range between 1000 to 1300 that it could be. I mean, the CC double bond alkenes is 1620 to 1680. Well, that's not there. So C double bond O and CO. So far, this is how you should be thinking, right? Your brain will be sort of working in the background as you're doing this question and these questions in general that, okay, so this might be an ester, but you have to keep an open mind. Okay, so that's V and O, W determined, C double bond O and CO. Lastly, we have the NMR spectra, and they've mentioned CDCl3. So that is the solvent to dissolve the molecule in. Solvents in NMR can't really have a presence of hydrogen because it interferes with the signal. So if you're wondering what CDCl3 is, just the solvent. And we can see that there are 4 distinct peaks. As explained in previous lessons, 4 peaks means there's 4 hydrogen environments. There's 4 unique hydrogen environments. Okay, so there's 4 hydrogen environments in the molecule. That's the first thing of NMR. The second rule of NMR that I discussed in another video is that the area under the peak, also known as the integration, is the number of hydrogens in that environment rather. So the integration is the number of hydrogens in the environment. So we can see 3H, 3H, and 4H. Now when you see 3H and 3H, that's always usually a good clue that it's probably going to be a CH3 because carbon bonded to another carbon with 3 hydrogens would give a CH3. But there's something even more prominent which sort of jumps out to me. So we have this. Whenever you see a peak that is in the 7 region or begins at 7, this is always a really big clue and a dead giveaway to a certain functional group. And that functional group is always benzene. This molecule definitely contains a benzene ring. So I'm going to start sketching out the things that we have now in blue. So we got a benzene ring. Now you're thinking, well, benzene, how on? Benzene has the formula C6H6. Surely the integration for benzene would be 6H and not 4H. Yes, that would be true if it was just a benzene molecule with nothing attached to it. So the fact that only 4 hydrogens are being detected in that environment tells us there must be 2 things bonded to the benzene, 2 other functional groups, 2 other parts of the molecule that are present. And what are those? Well, it's going to be that peak and that peak. So we have a benzene ring with 4 of its hydrogens left with 2 other things attached to the benzene ring. And we can see there's actually a separation in the benzene protons, which tells us that the benzene protons have got 2 different environments. And for that to work, for benzene to just have 2 unique hydrogen environments, there must be something attached here and something attached to the bottom. So that this environment here, so that those 2 protons, let's call them HA and HA, and then HB for the bottom ones. So HA and HA would be one of those environments, one of those peaks rather, and then HB and HB would be the other one. And that would show that there's 2 unique hydrogen environments within the benzene. So we have to determine this bit and this bit to finish it off. So before we go any further, let's just do a quick count. So we got C6, H4 for this bit, and the aim is to get to, if we scroll back up, we got to get to 9 carbons. So that leaves us with 3 other carbons to allocate, and we need to work at the number of hydrogens as well. So let's think about how we can put this into play. Referring to the data table, we have got a peak at about, that looks to be about 2.2, 2.3. And if you look at the table, we can see the proton NMR signal for about 2.2 indicates there must be a C double bond O present, which is good because we thought previously there's going to be an ester. There's a C double bond O there, and it's a singlet. So it's a singlet which has a integration of 3. So the only thing that can be attached to a C double bond O, which would produce a singlet with 3 hydrogens, is going to be a CH3. Okay, so we've got a CH3 on there. How is that? Because this would be a proton environment, and its nearest neighbor, the adjacent carbon, is a C double bond O. That doesn't have any hydrogens attached to it because it's going to be part of an ester group. And so therefore, it will not cause any splitting by the n+1 rule. So 0 plus 1 would make 1, and that would remain as a singlet. So we definitely know at this point there is a CH3, C double bond O, and an O present as well. Okay, so let's put this piece down. We won't put it onto the molecule yet, we'll just leave it there. So we know there's a CH3 and a C double bond O. Right, what about this one? So that is just under 4, so about 3.9. Again, you can see I'm approximating this because what you've got to be flexible. You're going to look at your data table and think, oh, right, I can see this environment at this point in the NMR spectra. Why doesn't it match it exactly in the spectra? Well, in real life, it doesn't always fit exactly to the data table. Okay, it will be in the approximately same position, but not always the same every time. So you've got to have a bit of flexibility. But the thing at about 3.8, 3.9 to 4.1 is a hydrogen attached to a carbon attached to an oxygen, which is definitely going to be. And we can see, again, it's a singlet. So for this to be a singlet, that would have to have the 3 hydrogens there to match the 3H. The atom next to this carbon is an oxygen, which doesn't have any hydrogens. And so this would produce a singlet. So now I can put this piece down. And you can see slowly this is beginning to build up. Before we go any further, let's do a quick check of the mass spec. So we know that the molecule has a mass of 150. So we better add up these parts to see how this is going. So we've got 6 times 12 plus 4 for the benzene part is 76. Remember, the aim is 150. So, you can see the way I'm thinking about this. I'm just putting the pieces of the molecule down like a jigsaw, like I've done in previous videos for these types of questions, because that's the best way to do it. Don't commit to a final answer until you have all the parts in front of you, and then you arrange them to make them fit. So we've got 76 from the C6H4. Then we've got 12 plus 16 plus 15 for this bit, which is 43. And then if we add those parts together, we've got 70 plus 40 is 110, 116. We're already up to 119. Now, if we take this bottom bit, it gives us 31, okay, for the OCH3. So 119 plus 31 gives us 150. So you think, great, I've got all the pieces of the molecule in front of me, and I've also got those parts adding up to the overall mass of the molecule, which is 150. So I just need to place them onto the molecule now to get this to work. Now, here's the thing. We've got a CH3 attached to an oxygen, so that's been confirmed, but we've just got a bit of a question mark over this part. So we've got a C double bond O. We know that it's this peak here, but in order for this to work, we've got to have it attached to the benzene ring. But if we attach this to the benzene ring, if we do C double bond O attached to this, that circle of the benzene ring, well, that's no longer an ester then. That just becomes a ketone. So there must be a CH3 somewhere else, because if I get rid of this part, then this can now connect to the benzene ring, like so, leaving a space vacant to put the oxygen there, and then that can be attached to the CH3, leaving a spare CH3 we need to put on, which is going to be that one there, okay? Remember that this one here, that at 3.8, 3.9, that must be this one. It has to be the CH3 attached to the oxygen, because that's the only thing that will create that chemical shift. So now I can build a better picture. We have the benzene ring bit is fine. This needs to be altered. That's fine. So it's going to be altered to this. So now that's correct. We've got a CH3 that has to go on the benzene somewhere else. And then we've got the benzene ring, which is fine. So if we bring all this information together, so in green, this bit, and this bit, we finish with this molecule, which I'll draw in black here. So the benzene ring, then on the top, we have C double bond O with the ester group. So there's the CH3. On the bottom, we have the CH3. And now what I'm going to do, which is what you should do in an exam situation, is once you've got the identity of the molecule, then to make life easier for the examiner when he's marking this, or she's marking this, is you need to circle the environments in your molecule and then label the actual spectra itself to prove that you have not cheated, that you have got the answer without any doubt whatsoever. And it just makes the script much easier to mark, and you're more likely to get full marks. So what do I mean by this? So this box here is the benzene ring. Let's call that A. So that's that bit there, A. Those peaks there, both of them. Then the ester part with the OCH3, that's the second environment. Well, it's actually that bit. Let's call that B, is definitely that one there. Then the last one, this the peak at 2.1, 2.2 is going to be this one, C, which means that one there is C. Now remember, A is actually composed of two peaks within the 7 to 8 part because there are two environments. So A is made up of, those hydrogens there, which I said was A, and I said B and B. But what I've done is I've just grouped those two individual environments as just one benzene environment. So if an examiner sees this, he can see your labels A, B, and C clearly marked on the diagram. And then, providing you provided sufficient explanation of how you got to that, you're going to get the full marks. So this, I think, was a 10-mark question. So, imagine getting this and then thinking, yes, I've actually got this right. I just need to explain what I've done. Right, I appreciate this is a difficult topic. This is why it comes at the end of the organic syllabus in whatever course you do in A-level, International Baccalaureate, Advanced Placement. It's meant to be hard, and that's okay. So please check out the other videos I've done on these mixed spectroscopic technique questions. There's a few attached in the description below. If you've got any questions about this one, please do comment down below and I will try and get back and help you as much as I can. If not, I look forward to seeing you in the next one, and thanks for watching.